Uh,
Good evening, everyone. Welcome to another session of Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCC PS ISC. It's my pleasure to introduce today's speaker, Professor Vaneet Aggarwal. He'll be speaking on average reward Markov decision process. Professor Aggarwal received the B.Tech degree in 2005 from IIT Kanpur and MA and PhD degrees in 2007 and 10, respectively, from Princeton University, all in electrical engineering. He is currently a university faculty scholar and professor in the School of Industrial Engineering, the School of Electrical and Computer Engineering, and the Department of Computer Science at Purdue University, where he has been since January 2015. Prior to this, he worked as a researcher at AT&T Labs Research, Florham Park, for 4.5 years. He was adjunct assistant professor at Columbia University, Vajra adjunct professor at IIC Bangalore, adjunct professor at IIIT Delhi, and uh, professor at IIC Bangalore, and visiting professor at KAUST, Saudi Arabia. His research interests are reinforcement learning, generative AI, quantum machine learning, applications of ML in networking, transportation, robotics, manufacturing, healthcare, and biomedical. He has received many awards, including 2018 IEEE Infocom Based Paper Award, 2021 NeurIPS Workshop Based Paper Award. He is currently serving on the editorial board of IEEE ACM Transaction on Networking and is co-editor-in-chief of ACM Journal on Transportation Systems. He is PC co-chair for GameNets 2024. He is also a 2024 to 25 IEEE ComSoc Distinguished Lecturer. Before we move on to the talk, we would like to request our online audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, feel free to unmute yourself and ask directly or type them on the chat box. We'll relay your questions. Over to you, Professor.
Thanks a lot for the introduction, and thanks a lot for inviting me. So today's talk will be on average reward Markov decision process, something that we had been doing for the last 2 years almost. So this is a joint work with multiple of the colleagues, Chinbo, who is a student, Shweta, who is OBDF fellow from ISC to Purdue, Vashim Mondal, who was former postdoc at Purdue, currently faculty at IITK, Bridge at UMD, Wes Suttle, and Brian at Army Research, Alec at JP Morgan, Amrit at Florida, and Dinesh Minocha at Maryland. So reinforcement learning is basically how we are learning with time. So how are we learning music with time? How are we going to evolve with time? How are we learning biking with time? How are we learning cooking with time? We did not learn these skills from when we were born. We try those skills, which is basically I take an action, I basically do certain thing, I have an environment, I'm seeing something, or I'm in a certain stage of what I have learned. I'm taking some action to basically retrain myself or improve myself. And then there's an environment that is giving me reward of how good I'm learning, or am I able to do the things and telling me this is possible, this is not possible. So reinforcement learning in a way is modeling how we are learning through time. So the key thing is agent is basically the person who is learning or the one who is making the decisions. It's looking at the state, it's taking some action, and then there is environment, which is all around us, which is giving some form of feedback, which is a reward, and it also gives how much you have learned or the next state. Okay. So reinforcement learning has had many applications. These are some of the applications of reinforcement learning, including healthcare, education, signal controls and decision control, recommendation systems, all the areas of math, physics, chemistry, natural language processing, computer vision, robotics, games, and the financial or computer systems. So it has been widely applicable in many areas. And these are some of the applications. This slide I've taken from a course by Chaba. And so these are biased based on what he thinks are real world applications. So there would be many that are focused on DeepMind and Google. So video compression on YouTube is, according to him, using reinforcement learning. We already know competitive programming, compiler toolchain, and many of the other things have been using reinforcement learning. Even in industrial automation, cooling the internal of buildings, getting this air conditioning, heating, and all those things are using reinforcement learning. Inventory management, that's a problem that can also be modeled as a learning-based problem, where action is determining how to manage the different resources. Other than that, GPT is describing the role of RL. By the time this slide was there, GPT was not using RL, but by now we know it is using RL in some forms. So it has had applications in many different areas. So something that we should be working towards to improving the performance. All right, so we'll talk about what are being the different models in reinforcement learning. So one of the model that has been widely studied is called a discounted reward model. So we have to choose an action in reinforcement learning that optimizes the rewards. RT is the reward that you get at time t. In the discounted reward setup, we maximize the sum of discounted reward. What it says is reward at time t plus gamma times reward at time t plus 1 plus gamma square times reward at time t plus 2 and so on. Okay. So the objective is a discounted reward, and based on that, we decide what is the action to choose that will maximize this. Average reward does not discount. So it is sum of rewards, but then since it can go very large, we normalize it by 1 over t. Okay. So this is the notion of average reward. Then the third is an episodic model. Episodic model is similar to an average reward setup, but what happens is the state resets after a certain time. So think of this type of example as playing a chess game. And after you have won or lost, it resets because you start from very scratch. So it has been a common model in terms of gameplays and things, while the models discounted and average are a single trajectory. You're learning over a single trajectory, like learning through your life. Okay, so discounted reward has had applications. It is modeling, of course, some of the financial type of thing where we discount the value of money, and that is where one of the application that had been proposed. But for most engineering applications, it has been an artificial construct because most of the metrics for engineering had been throughput, latency, and different types of notion, which are inherently not discounted. We are not discounting the future in many of these applications. We are talking about total revenue that I can get or things of that nature. The reason discounted reward had gotten popularity has been it is easier to analyze mathematically, and that is because it has nice properties of contraction and other things, which actually make the mathematics easier. And that's why most of the theoretical results have been in this model, and most of the algorithms, if a person uses reinforcement learning, with high probability, they will get the models for the algorithms implemented for the discounted case. Use gamma very close to 1. Most of the people who would have used reinforcement learning algorithms that have been implemented, they would be using gamma as 0.99 or 0.999. So they inherently want average, but they're using discounted because that is where the algorithms are. And other thing, this is an analysis-based approach. The discounted analysis typically is assuming an access to a simulator. There have been some recent analysis that are not. So it's basically assuming that there is a distribution, I can reset to the distribution, or I can get samples from a certain distribution. So there have been some assumptions like that, which limits the analysis of the discounted rewards. Episodic model, it's not the focus of our talk, but it has had applications in video games, chess, where the game can restart. So it is modeled as you have certain thing and then you go across time. So you can learn across multiple games. While as I mentioned, discounted and average are infinite horizon, a single trajectory which you are learning through. Average reward is relatable to most of the engineering applications. They are harder to analyze, and typical analysis has been on single sample path. And this is why average reward is basically becoming more popular. It has been open since a long time, and algorithms in this area are only starting to study very recently. Okay. So this is basically, in the previous slide, this is to substantiate, because coming from me saying, oh, discounted reward is primarily artificial construct, people will say, okay, who are you? So this is basically a slide saying, okay, there are bigger people who are saying the same thing, that discounted reinforcement learning has an issue when you are doing the parameterized setups, and even they are suggesting that people should look at maximizing average reward for, especially for applications where you have continuing tasks. Okay, so this is basically just, I've copy pasted the abstract from archive. So let us understand the key difference between average and discounted from an application. So in this figure, I have 9 states from 0 to 8. There is an action only at state 0. You can go either left or right, okay, which is the action you can choose in this state. In 1, whatever you choose, you will go to state 2. Whatever you choose, you will go to state 3, and so on. So in every other state, the decision is fixed. The reward is 0 unless pointed. So the only rewards you get is, if at 0, you go to left, you get a reward of +1. If you go to right, then here you will get a reward of +2. So the basic idea is you get an immediate reward of 1 and keep going this way, or you get a delayed reward of 2 and keep going this way. Means every 4th time you are getting a reward of 2. Which one should you be preferring? So if the discount factor is small, then a small, we can compute how a small gamma cube less than 1 by 2 or something like that. So basically, given a discount factor, with discounted, you might choose this trajectory and keep on getting an average reward of 1 by 4, right? So 1 by 5 probably, but proportional to 1. Okay. If you go towards the right, you will get 2 delayed. So discounted will choose this for a small discount factor, and the average will choose this. So that is the key thing. If you are going enough across time, then you want to be hitting 2 again and again rather than hitting 1 again and again, right? Because the first few should not matter. So that is basically the idea. Why we should be using a discounted on an average. If based on your application, this path is better, go ahead, choose discounted. But if this is better, then average is probably a better notion. Okay. So we already have results on discounted. Why can we directly use them for average? The thing is, as we noticed in the definitions, the only difference is gamma. I can take gamma to 1, right? Or I can take limit gamma going to 1. Why does that not work? Right? Or why does such simple things not work and we need a new analysis? And the reason essentially is, if we are taking the discounted, so we have a value function which is measuring my sum of discounted rewards. The metric I'm optimizing in discounted is I'm finding a policy that optimizes my value function. Okay, I've added 1 minus gamma because I will be taking the limits and I want limits to be stable. So discounted essentially does this type of metric. And if I'm implementing the optimal policy for this for any gamma, and then I take limit gamma going to 1. That is basically how I would take the limit of an discounted at gamma going to 1. The average will be different. The average will be, I would take this limit inside. Okay, so I'm finding the policy that maximizes my sum. So argmax over the limit of this. So limit and argmax gets replaced. So the problem is not the same, and the two are not commutative. Okay. So other intuition is most of the algorithms that have been designed for discounted actually become unstable as gamma goes to 1. So at gamma equal to 1, there is an instability. Even contraction mapping doesn't work. So many of the results actually stop holding. They have 1 over 1 minus gamma to the higher powers when you talk about their sample complexity type of things or regret. So, and the key thing is the estimator for the value function can become unbounded, and the error in the value function estimation has a complexity, has a term of 1 over 1 minus gamma. So you can't even estimate a value function with a bounded gap. And that is why you cannot take a discounted algorithm and then convert it to an average. The other thing is technical, in a sense that discounted results are typically assuming access to a simulator, but in average, we don't want that. Since everything is equal, we don't want to restart or take samples from some other thing, IID. So we typically don't make such assumptions when we talk about average. Okay, so there have been many RL algorithms that, yes. No, you care whether it's biased estimator, but discounted typically assume access to simulator. Average, we don't want to make such assumptions. We want to get everything from a single Markovian trajectory. Okay, so typically when people consider average, they do the analysis more carefully in terms of not having access to the simulator. Even though in discounted, there are now results that also work with Markovian samples. Okay, so this is giving a standard view that there have been many reinforcement learning algorithms for discounted case in the literature, and these are some of the key ones. So reinforcement learning algorithms are divided into model-based and model-free. Model-based algorithms are where you learn the model, the probability distribution of the evolution, and then use that for your system. Model-free is you don't learn the system parameters and directly make decisions. And most of the applicable ones for in the recent years have been in model-free. Chess game was earlier solved in 98 using model-based algorithms, but AlphaGo was in 2015-ish solved using model-free algorithms. And they are divided in terms of value-based or policy-based algorithms, and some of the algorithms come in between. One of the key things in most of the algorithms here that you would have used or people would have used is that they are assuming some kind of neural network or some kind of parameterization for scalability. So parameterization is important for scalability, and that allows us to go to large state spaces, large action spaces, and things of that nature. Okay. So this is basically saying tabular setup is limited for large state spaces. So we need some form of parameterization to have scalable algorithms. One form of parameterization is, example, neural networks. So most of the algorithms that I had in the previous slide have parameterization, although they were for discounted rewards. So algorithms and guarantee with parameterization are important, which is the focus of the talk. So we've basically given a broad summary of the area. Now we'll go over the exact model that we will be considering for our work. Any questions on the overview? All right. So we'll go over the model that we will be using and what will be the key challenges there. So, okay. So we are assuming an ergodic Markov decision process. So what that means is, given any policy, the Markov chain that would be made will be ergodic. And a parameterized policy. So parameterized policy is determined as pi theta. Pi is my policy, theta is the parameter. So think of theta as the weights of the neural network, and pi theta becomes the policy, which is determined by the neural network with the parameters theta. And a reward is determined by R. So J is my overall objective, which is my value function, which is the expected value of the rewards, and the expected value over my state going based on the policy and action being taken based on the policy. Okay. So expected value of reward that you are getting for that policy, which is determined by pi theta. Okay. So I can basically write this in the vector notation, which is intuitively some form of steady state distribution in a product with the rewards. Okay. So the regret is the key metric that we will use to see how good our policy is compared to the best policy. And the way that is defined is we have J star, which is the policy, not in the parameterized class, but in the complete policy class. So the policy that achieves the best value function, the best value function achieved by any policy is my optimal. Okay. Note that in the optimal, we are not restricting it to just my policy class. My policy class is pi theta, where theta is basically parameters of the thing, but the optimal is general. So this was my overall, but I could have achieved at each if I knew everything. And this is what I'm getting, the reward at time t, which is based on the state at time t and action at time t. So this is what I'm getting. This is what my optimal is if I knew everything. The difference of them summed over time. That is the regret metric that we will be comparing, that will be taking as benchmark for our results. Any questions at the objective and the problem formulation? Okay, so we are maximizing the reward, the expected value of reward, and we are measuring with respect to, suppose if we knew everything, what would be the best policy compared to what I'm getting. Of course, this is random. Even if you fix the policy and fix the, there is a distribution of evolution. So regret t is a random quantity. So our metric will become expected value of regret rather than regret. Right. So typically in the literature, this notion is called a pseudo regret, and expected value of that is called a regret. Okay. So the first thing that we'll go over is trying to understand more about the problem of average reward. What is the key difficulty? One of the easy thing in discounted is we could have Bellman equations, and Bellman equation gave us a contraction which helped us solve things. In average, there are also Bellman equations, and these are the Bellman equations written. So in discounted case, V function and Q function have meaning. You might have heard about value function and state value function and state action value function, which are V functions and Q functions for the discounted. For average, they have no physical meaning. So what it says is there exists a function V and a function Q that satisfies these two equations. Here, Q is a function of V, here V is a function of Q. So it basically relates to a joint fixed point among them. So it only says there is a V and Q that satisfies these equations. Okay. One interesting thing is these two are linear equations. There's no unique solution for these equations. As an intuition, see that if Q and V satisfies these equations, then Q plus C and V plus C will also satisfy the equations. Okay, I add a constant here, the constant here, constant here, constant here, it would be fine. Okay, so there's no unique solution. And in order to get a unique solution, we have to make another assumption. We basically normalize, let us say, oh, let's say find a V function such that expected value of V is 0. Something of that nature. So you basically put that to get a unique solution. And if you do that, then this is that choice that satisfies these equations. Okay, that's why I said one possible choice. Of course, these equations have infinite values of V and Q that satisfy it. So intuition wise, value is sum of rewards given the state. That was how it was discounted with the gamma. The difference is I have to subtract j theta, and same here. You have expect value of reward given state and action. I have to do subtraction to make a unique choice. All right. So we already saw that the V and Q there were not fully unique. They could have a shift by constant. So that's why we define something we call as advantage function, which is A, which is defined as Q minus V. So the reason we define as Q minus V is up to shift, then I don't have to care about it. I can choose a choice up to lateral shift of V and Q. That will cancel out when I do the difference. Okay. So We are assuming ergodic Markov chain. One of the key things that ergodic assumption gives us is that mixing and hitting times are finite. So this is the definition of mixing time, which is common in the literature, which is this is my P transition probability going by a policy pi theta. So if I take P to the power T, I should converge to a steady state distribution. Right? That's the policy of ergodic. P to the T will converge to the steady state distribution with this type of notions. So how fast does P to the power T converges to the steady state distribution? Okay. So how fast does a Markov chain converges to steady state distribution with the policy being pi theta, and then I will maximize over theta and assume it is bounded. But how close we have achieved to the steady state distribution, I have to define that gap. And that gap is typically taken to be 1/4 in the literature. You can take any epsilon, but if that epsilon is 1/4, it's called the mixing time. There's a T-mix of epsilon, and T-mix, if it does not say epsilon, then it is basically 1/4. And I'll explain why the result with 1/4 and why it is a common use metric. And T-hit is basically saying that the steady state distribution should not be 0 for any state. Okay. So it's basically capturing that aspect. Although T-hit in many cases is not needed, but it's still assumed to be finite for ergodic. So mixing time, it basically characterizes how fast MDP converges to steady state distribution. One of the key thing is, if you define the mixing time like this, and T mix as the max over theta, T mix of theta, then after time T, your probability distribution gap to the steady state goes as order of 2 to the power minus T by T mix. So if my T is of the order of T mix times log T, this will be 1 over T type of thing. So by just taking a time which is T mix log T times some constant, I can decay the gap between P to the power T and steady state distribution. So I've almost achieved steady state distribution with a very small correlation, which I can control based on how large is T compared to T mix. That's the mixing time. That's the max of theta over this. Okay. Because I have to do for any policy. So, all right. This is already called geometric mixing ergodic. So I'm not assuming any order on that. But this definition, this assumption that T mix is finite already assumes that. We're not assuming any order on T mix. T mix is something that is finite. Okay, we are not having T mix scaling with T. T mix is something given. Yeah. T mix is max of theta over T mix theta. That for every policy, the worst case T mix theta. Yes, T mix have time. T mix is time. Max theta, T mix theta. Over theta. So mixing time for the worst policy. Okay. So the algorithm we are going to start is a very simple algorithm. It's basically a form of policy gradient algorithm where theta is updated based on the gradient of my value function. The simplest gradient descent type of algorithm we can come up with, right? So the key question now is, how do I estimate this gradient? Okay. So in discounted, we had all these algorithms like reinforce and a bunch of other algorithms which are focusing on how to estimate the gradient for the discounted case. How do we do them for the average case? So in discounted case, we could get samples from get independent samples, and we could estimate the gradients. However, the key thing is we have a single trajectory. From a single trajectory, the samples I'm getting are not independent. Okay, they are Markovian, but if I take samples from my past history, they will not be independent of each other. And I have to get value functions from them in order to estimate the gradient. How do I estimate basically these gradients from my Markovian trajectory? That is not a straightforward problem. Okay. So now I think we can go over what the outline is. We'll go over an approach for gradient estimation for this problem. We'll then improve the results to get better results using variance reduction. And these algorithms will use mixing time, and then we'll give approaches of how to remove mixing time from the algorithm choices. Okay, but the main topic has been how to get these sub-trajectories from the Markovian data. Okay, so the key question was, this is my gradient estimator, which I can write as expected value of this. The question is, how do I create unbiased? I'll be doing Monte Carlo, of course, right? I have expected value. I will be taking finite samples and taking their averages. Now the question is, how do I create unbiased sub-trajectories to be able to get this gradient? Okay. So I need them independent so that I can use law of large number type results. But it's a single big sub-trajectory. And the key thing is basically the use of mixing time. So what I'm doing is I am taking my time, dividing them into a bunch of episodes, which is typical in reinforcement learning or any algorithm. You'll be computing the gradient based on the previous episode, the previous H time, and then using that for doing the policy update at the next time. Okay, so you have a previous H length of data. So this is entirely showing my previous H length of data. My question is, I have to create independent sub-trajectories from here. We already know that if I take t mix times log t time, then the future and past are kind of uncorrelated. After t mix log t, none of the samples will be related. That is the aspect that I will use to basically create independence. So n, think of n as like order t mix times log t, okay, where the past and future will become independent. So I have to wait for a certain state. So this is my entire previous H length. I wait to see the state. Let's say I have to estimate the value function here, which is only a function of state. I wait to see the state S, then I take a sub-trajectory of length n. I need a large enough sub-trajectory so that I can even estimate things fine. So I sample a n length trajectory. Then I wait for order t mix, actually order t mix times log t. I wait for that. And the reason is, after this, I'm back to a stationary distribution. So anything in the future here and anything in the past from here will become uncorrelated. Of course, there's a correlation of 1 over t to the power something, but that's as good as basically becoming uncorrelated, approximately. So I wait for that time, and then I wait to see S again, and then take another n length trajectory. So what will happen is this sub-trajectory and this sub-trajectory will become almost independent. Okay, and I keep this procedure to basically find my independent sub-trajectories. I use these sub-trajectories and then get the Monte Carlo estimation from there because they are as well as independent. Does it make sense? Yes. Can you please repeat? Because I'm estimating things at a given S or a given S and A. So I have to do a Monte Carlo on that. So I will be doing on multiple S's and then doing the averages over them too. But a value function will be a function of state. Okay, I'm learning something which is a function of state. Okay. So this will make it clear. I'm basically learning the value function as a function of state. I'm learning Q function as a function of state and action. Then I'll be learning a differencing them to find the advantage function. And then my estimate will be the gradient estimate, which will be based on these things. So I can do all those things once I've come. The main thing is to get the sub trajectories, which I'll get from what I mentioned before. Yes. Yes. So this is basically what I'm doing. I'm doing it from TK to TK plus 1 minus 1. So only S and A, I'm concerned with this STS and ATs. So you are not still not doing over infinite. You are only doing over the state and action that will be visited. Right. So you can basically choose a smaller subset of them. Right. But yes, dependence across that does not matter because This is only sum over time. Those are summed, so you can get independent errors. What matters is basically this estimation, A hat compared to A should be good. If A hat compared to A is not good, that is what is the bigger issue. Because rest is summation. Okay. So for a given S and A, my advantage estimation error goes like 1 over square root T. So what it says is if I use this approach, I can get a very good advantage function estimation. Okay. And since I can get an advantage estimation, if you see here, my average was based on the only thing that I cared about was advantage estimation. If I can do the advantage function estimation well, then I can get a very good gradient error. And gradient error goes as 1 over square root T. Okay. So using these errors, let me see, I can get the overall result of regret. And the regret is basically composed of different terms. I'll basically explain some of the key terms. One of the term is epsilon bias. Epsilon bias is intuitively, I took a policy which was parameterized. That policy class may not cover everything, may not cover every policy. So it's basically richness of the approximation of my parameterized class. Okay, and that term will come linear, that you can avoid because every function cannot be represented by a neural network. Okay, so this is basically that term that is inevitable because of my parameterization. And this is related to T-mix. The other key term here is this T3/4. Rest are all small. So your regret is order T3/4 with these terms. And the key assumptions are standard. We are using an ergodic MDP. We are assuming Lipschitz and smooth assumptions in parameterization. This is in English, this is in math in case you are interested, but I'm sure we won't be. But yes, in case I've written the complete thing here. So we are assuming Lipschitz and smooth parameterization. Compatible transferred error is basically the richness of the policy parameterization, which is what I'm assuming. And we are assuming a Fisher non-degenerate assumption on my parameterization. That second order things are fine. So using that, we are getting this T3/4 type regret guarantee. And the analysis uses some of the tools that we are skipping with time. So the key intuition is why are we limited to T3/4? In order to understand that, we go back to our result on the errors. We did the gradient estimation error with error of 1 over square root T. And the key thing here was the square error is bounded by 1 over square root T. And in the later analysis, we will need the L1 norm here rather than the L2 norm. And when we do the L1 norm, we have to use this type of inequality, which will change this 1 over square root T to 1 over T1/4, which when multiplied by T will give you T3/4. And that is basically the limiting factor. So given all the theory, the key thing that limited to T3/4 is basically this error that we were doing in terms of squares. And this is a fundamental bound. We won't be able to improve directly using these algorithms. So the current approach of proof will not work, even if you do something better estimation, because this is the best we can do using such approaches. So we'll now describe another approach to have better results. So before we go further, so our work was the first work for general parameterization, which can give T3/4 regret-free for ergodic model-free type of results. So none of the works before had worked on general parameterization type results. Okay. And we are not getting best because we know even standard policy gradient is not optimal even in the discounted setup. Okay. State of art is one of our paper, which will be which is in AI stats this year, which is based on accelerated MPG. And there is another paper in ICML 2023, which is based on normalized policy gradient. So those are basically optimal for discounted. Question is, can we use ideas from there for average? And that is basically the next work. And the key thing there is, so in the previous part, we had a fundamental bound, which actually we could not improve. And the reason we could not improve was we were only using the previous trajectory for estimating the next. If you're using the previous, law of large number says you cannot estimate it better than 1 over square root of the previous trajectory, previous sub-trajectory. And previous sub-trajectory was order square root T. And 1 over square root of square root T gave us a fundamental bound, which we cannot improve. So you can prove if you go episode by episode and do the gradient only based on the previous episode, T3/4 will be a lower bound. If I have to ignore that, at any time, I have to use my entire past, not just my previous episode. Okay. What is the way such that I can use my entire past? One of the way I can use my entire past is something we call as momentum. Momentum is I basically just don't use the previous gradient. I use the gradient from before and do a convex combination with the current gradient. That way, I'm not throwing the past. If I don't throw the past, at least I have a lot of time in the past to take care of. And that is the key approach that will help us get the results. So the key algorithm is I'm basically computing this gradient based on what I basically mentioned before. Then I'm basically doing a momentum, which is 1 minus eta k taking something based on this. Sorry, 1 minus eta k the past and eta k times this one. Okay. And then I'm normalizing the theta. Okay. So theta I'm basically doing based on the normalized addition. And this type of approach has been shown to improve the regret to t to the power 0.6. This is not using any second order information, just using the momentum and normalization. And then I can use a Hessian based technique, and Hessian based technique can go to square root t results. Given the time, I'm not going over what is the variance reduction, but basically it is a second order approach. B is my Hessian, and I estimate the Hessian vector product, and then I can use that for variance reduction. Okay. The key issue with what, yes. This one, this was there even in the previous one. That is your length of the next episode. So the gradient you are estimating based on the previous trajectory or the current trajectory. So it's not the entire thing. Gradient is based on the samples. So this is the new gradient. I'm using momentum to take care of the previous, but I'm not taking care of the past for my gradient computation again. And the reason is that was using a different policy. My policy changed across the episodes. Important sampling. Yeah, then you have to take care of all those important sampling samples to convert the previous policies to the current policies. But this is kind of doing that in a way to convert the previous by discounted them. That the previous were still close by, so let me start discounting the previous. So it's the same intuition. If you do a precise analysis of important sampling, that might work too. But here we are ignoring that to basically do this momentum approach. So your intuition is right, but the main thing is again the same, that my policies were different, so I cannot use the entire thing. And the way I use the previous thing is here using. Which one? H is the length of the previous time episode, which is tk plus 1 minus tk. We keep it as constant, which will be order square root t in the analysis. Okay. Sorry. Okay. So this approaches that we mentioned so far are using the mixing time in order to create sub-trajectories. So we don't want to do that because that may be limiting. Mixing time in many cases, we don't even know, right? And if we go to continuous, mixing time will also be may not be known and the bounds may be bad. So this is basically saying why the previous approaches do not work well. So the earlier estimation procedures needed my h, which was the length of each of the episode, to be very large. So even if I have mixing time and hitting time of 1, the requirement of h was actually 6.6 times 10 to the 9. Even before. So we don't want, if the gradients are big, we don't want it to go large. So we are bounding basically the deviation of thetas. Okay. So if we have hitting time of 10, this is basically saying as I increase the mixing time, how much was the H needed? And this basically says you need a lot of H. What that means is the previous algorithms that I talked about, very good in theory, may not work in practice. Okay. So in order to do that, we need an algorithm that works. And luckily, there is one approach, which is to take my samples directly from the Markovian data without creating sub-trajectories. And that approach is called multi-level Monte Carlo approach, MLMC in short. So this is just explaining what is MLMC in short. So what this will be doing, this will not be creating sub-episodes. This will be taking the entire time directly and creating the estimate at any time based on the entire past. So this is only, I'm explaining how to use MLMC to compute gradients, not our policy gradient alone. So NT is the samples that I'm using to estimate anything in the tth iteration. So think of an SGD loop going, and I have a tth iteration, and in tth iteration, I use NT samples. Okay, and this is one of the sample in the tth iteration, which is going from 1 to n1 for the first iteration, 1 to n2 for the second iteration, and so on. Okay, so I define the average of the gradient with 2 to the power j samples in round t. So in round t, I'm using, let's say, 2 to the power j samples. Then my gradient estimation is average over 2 to the j samples of the function gradient. Then MLMC estimator is given something like this. So the intuition of MLMC is if I have to do expected value of yt, I write it as expected value of y0 plus y1 minus y0 plus y2 minus y1 and so on. So it's basically the chaining sum, which is what is kind of happening here. So I'm basically using that and JT, which is the time I'm sampling in each epoch based on a geometric distribution, exponential of geometric distribution. And I create my MLMC estimator, something like this. Of course, it's hard to get intuitions just looking at it, but let's see what is happening. So the computation of MLMC estimator only needs estimate over this 2 to the j estimates, which is I'm only using NT, which is 2 to the power JT. JT is geometric distribution, so it's not basically increasing with time. Of course, I need a condition which is 2 to the power JT less than T, which means J will be maximum log T. I will be bounding there. So, and NT that I'm choosing, which is 2 to the power JT, will be independent of the previous. So that independence will be used in my variance reduction. And the estimator is biased. It is not an unbiased estimator, but it has the same bias as simple average of noisy gradients. Okay, and the the number of samples n is shown here that it is only order log t. So the number of samples I need is only order log t in each SGD iteration, and I can compute it very well. Okay. So this is basically changing the notation. So we have a Monte Carlo estimator in our thing, and drawing from geometric distribution does not need the knowledge of mixing time. And I can use, there have been some approaches like ADAGRAD that have been used to reduce the variance in this approach. So what we did was we used this type of approach, MLMC estimator, to estimate the gradient for our Markovian data. And used a actor-critic based approach to do that. So this is basically average reward via multi-level actor-critic type of approach, and we could get the same T3/4 regret guarantee. Okay, so algorithm is independent of mixing time, so it is scalable. The regret in terms of mixing time, so this was the previous paper, that the first paper that I explained, that has mixing time square, this is mixing time square root. So it also improves in terms of mixing time. There's no dependence on hitting time anymore. Can we improve this further? We still have a gap left, right? And that is basically our final thing. So what are the ways we are using to improve it? It's the same intuition. This one was using actor-critic, which was using policy gradient based thing. Now, in order to improve this, we have to use natural actor-critic because we have to use a Hessian based term. So I use a natural policy gradient type of estimation. The critic has to be estimated, which was based on TD error type analysis. And this gives us the critic and average reward estimation. And this is for reference, the vanilla PG, which will be used here in the natural policy gradient. So can't go over too many details for the talk, but let's see the key things. Even in NPG, we have to estimate the gradient. So we are using MLMC. Okay. NPG direction, we have to use the idea of acceleration, because even in the previous case, acceleration gave us advantage. So in every of the step, every of the directions, we are adding an acceleration step. Okay, acceleration is this nest of acceleration, which is momentum. And both in the actor and critic, both updates we added basically the acceleration, both in reward updating, critic updating, everywhere we basically added the acceleration. Okay. And the key novelty is the MLMC estimator now uses a momentum term for variance reduction. We removed the aspect of adagrad. So the first approach for variance reduction needed adagrad. We changed the adagrad to now just use momentum. Such an acceleration approach had been recently proposed that replaced the adagrad with momentum, but the current papers required the knowledge of mixing time. We changed that analysis approach completely to not even use mixing time and use all these geometric based updates. So we improved even the state of art for stochastic optimization over a Markovian data. Then gradient estimation is biased here because of all the errors in the reward and critic. So you cannot get the standard SGD based analysis directly. So there were novelties there. The other things which could be parallel. So if you're doing a simple TD learning based approach, the current state of art was 1 over square root t. We showed that if you do momentum acceleration, even TD learning error changes to 1 over t. Okay. The other new result that we have is if you are doing stochastic strongly convex optimization, nothing to do with RL, but this will be needed for our NPG update. So our NPG natural policy gradient update is actually a strongly convex optimization with stochastic. So stochastic strongly convex optimization, if you have with Markovian data, we show that we can achieve 1 over t convergence rate without knowledge of mixing time, without using projection operators, without assuming bounded domain or gradient. So we removed all the assumptions. So such a result was there, but with tons of assumptions. We basically removed all the assumptions and we showed that it holds in general using these approaches. So this is basically the summary. This was our first work that I presented, which was taking the episodes of H, learning over the previous one, which gave us T343 grade bound. The MAC multi-level actor critic was the previous work where we were using the standard actor critic with MLMC, which achieved T3/4. This work achieves square root T regret. Okay, so towards the end of the talk, let's see what all we learned. We had the first work on regret analysis of average MDP in the parameterized setups. We gave the first results for gradient estimation approach, which was dividing the time into episodes of length h, and then using the previous episode and computing the gradient based on creating the sub-trajectories. And that achieved a T3/4 result that was presented this year in AAAI. Then we improved the results by considering the momentum-based approach. This is existing on archive and submitted. Then we removed the mixing time assumption for the algorithm. The T3/4 result that I mentioned will be presented this month in ICML. And the square root 2 results is now submitted and it will be on archive soon. Okay, so there are tons of open questions this type of topic leaves. One of the key is, one of the thing I would also like to point is in the last work, we can also go to continuous states and continuous states, because the mixing time can be defined even for continuous state. And we only need mixing time to be finite. As long as you have a continuous Markov chain with the finite mixing time, the results still hold. So nothing changes. So, and that is true only in the last result, in the MLMC based things, because in MLMC mixing time could be defined for that, and we are only using the steady state results, which hold for continuous states. While the first set of results could not hold for continuous states because we have to learn it at every state and action. Okay, so one of the key assumptions we used here was mixing time to be finite, or we assume ergodicity. It has been known that the key condition needed for coming up with optimal policy is not ergodicity. It is something we call as weakly communicating. This is the technical definition of weakly communicating, which essentially means you can have transient states, or you can basically have under certain policy getting a bunch of separate Markov chains. So for example, this is one setup where you have two states. In each state, there are two possible actions. One is solid and another is dashed. From here, one is solid, one is dashed. There exists a policy where from state one, I choose this action. From state two, I choose this action, which is basically I remain in the same state. If I choose that action, I never go to the other state. So it is basically not becoming an ergodic Markov chain. That is still a weakly communicating, and there exists, this should have been fine, but how to come up with policies is an open question. This is, and there have been some results, people have been coming up in different type of setups, but here those directions are still open. Okay, other aspect is constrained MDP. So here I did not consider any constraints on the decision process. So for constrained MDP, the best results that we have, so we took the first algorithm that I presented in the talk, which had T3/4 regret bound. We could use a primal dual type approach on top of that, and we can get T4/5 regret bound. And that result is already on archive. The lower bound is again security, so there is a significant gap. And also, even in the tabular setup, there is no work on model-free weakly communicating CMDP so far. So this direction is completely open. Okay, so not just parameterized, even in tabular, there is no work. So those are some of the things. So we have a monograph on the topic of average reward CMDPs, which is online on archive. We posted it a week ago, and it will appear soon in now Foundations and Trends in Optimization. Might be a good reference if you want to understand the key challenges in CMDP. We cover model-based as well as parameterized model-free type setups. We are currently starting to write a book on foundations on reinforcement learning, and we are focusing on discounted and average reward as a treatment holistically on discounted and average, the theoretical treatment on them. So we have written so far 2 chapters. Once we have a significant volume, at least 25% of the book will put our current versions on my website, and we'll keep updating. So that is something that we are working towards in this area. So any questions?
Thank you, Professor, for an informative talk. Are there any questions?
Yes, sir. So as you saw, first was using this SGDE with acceleration, so optimization a lot, right? Because you have to come up with all those things. Second is stochastics, because you're learning things over a stochastic noise or a Markov noise, right? So if you think about Bayesian optimization with stochastic noise, those are parts of it, right? Because as I mentioned, even in the results here, sorry. So right here, even stochastic strongly convex optimization or Bayesian optimization, we had to get results for them. So we had to come up with results for stochastic optimizations. We had to take the finite samples. We had to take care of biases. So the combination of probability and optimization tools, or stochastics and optimization tools, are the key ones that are used in this type of research.
If there are no more questions, we can close this session. We have refreshments outside. Please enjoy the refreshments and have the conversation outside. Let's thank the speaker.
Thanks a lot.